Hello, everyone. Good evening. Right. Okay, people are gathering. Can people hear me? Okay, good. That is good to hear. So today we continue talking about integration and we continue talking about centers of mass. So this is the third webinar on the same topic. So if you have any particular questions, I'm happy to discuss them because the questions will be somewhat similar to last week's, slightly more complicated, and or some are easy, some are slightly easier. So feel free to ask any questions. Okay, I have the chat open. Feel free to speak as well. Why not? There's only 9 of you today for now. And I think we can start how to integrate 1 over x. Well, I don't believe you need to integrate 1 over x. There's no questions in the assignments where you need that. But happy to do that for you. We've deliberately not included the integral of 1 over x because you haven't done the logarithms yet. Okay, so I'll show you. And share. Okay, so you should be able to see my screen. If you don't see my screen, let me know. So if you have the integral of x to the power n dx, this integral is x to the power n plus 1 divided by n plus 1 plus c. But this is only true if n is not equal to -1. So n equals, because if n equals -1, this is this is division by 0. You have division by 0, which is impossible. Okay. And so what happens when n is -1? Well, we know from differentiation that the derivative of the logarithm function of logarithm x is equal to 1 over x. So in fact, we use that because the integral is the antiderivative. So the integral of x to the power -1 dx is a special case, and it's equal to logarithm of modulus x plus c. Okay, so that's about it. I won't go deeper than that for now. Or, well, it's the same. You can write it in a slightly different way as log integral of 1 over x dx equals logarithm of modulus x plus c. The modulus is here because 1 over x can be negative, but logarithm, you cannot take a logarithm of a negative number. So yeah, that's about it. Okay, so let's go to the first question. The first question, so we started with physics, and the last few questions will be on maths. But again, physics is interlaced with integrals. This particular topic, there's a lot of integrals. Okay, so we have a rope. So this is our rope, and we have a mass, 100 kilograms, hanging from the middle of the rope. The rope is 4 meters long, and we can see that the rope deforms as a result by 10 centimeters. So 10 centimeters is the vertical distance from the point of where the rope is attached to the bottom, the lowest part of the rope. The rope is light. So that means that if there was no mass, the rope would be perfectly horizontal. And okay, that is only true for ropes of mass 0. Yes, so it's impossible to have a horizontal rope. Try to convince yourself that a horizontal rope is not possible. Or because any rope has mass and the weight acts on the bottom. And if the rope is horizontal, that means the tension is strictly horizontal. So W is not compensated by anything. Okay, so the tension forces in the rope cannot compensate W because they're perpendicular. So any rope, no matter how light it is, will always have some kind of slack, even with infinite tension, if that exists. But here we say it's a light rope, so it's approximately horizontal with no mass attached. With a mass attached, it is in the shape of well, 2 pieces of rope, basically. Okay, the center part of the rope is displaced by tension. Find the tension in the rope. So we're going to draw the central point. We're going to draw point A and draw the forces acting at point A. And there are 3 forces. First, there's the mg force. And then there's a tension force. And there is another tension force. So this is the tension in the rope, and mg. We're gonna split the tension into 2 forces. And we're gonna split this tension into 2 forces, into components. Okay, and if this angle, let's introduce this angle. We call this angle theta. And this is the angle theta. That means this is T cos theta. And this is also going to be T cos theta. Cos theta. And this is going to be T sine theta. Sine theta and T sine theta. Sine theta. And well, we know that the rope is in equilibrium. There are 2 conditions for equilibrium, which I mentioned in the assignment. And one of them is that the forces have to be equal. So the vertical forces have to be have to total to 0, and the horizontal forces total to 0. The horizontal forces being equal gives us nothing because it's literally T cos theta equals T cos theta. So we don't even need to write that down because it's obvious. It doesn't give us any information. The vertical forces, however, give us new information, which is T sine theta plus T sine theta is equal to mg. And is going to be 2T sine theta is equal to mg. Okay, and T is equal to mg divided by 2 sine theta. Sine theta. So we only need sine theta now. But to find tension. But we know that this is 10 centimeters and this is half of the rope, so it's 2 meters. So we can draw it like this. So this is 10 centimeters and this is 2 meters. Okay, so this is 200 centimeters and this is 10 centimeters. So I'm drawing this part. I'm drawing this triangle. Now, this angle is theta. So if I want to find sine theta, well, there are different ways I can do it. I can first use the Pythagoras theorem to find the third side. That's obvious, yes. I'm sure you all can do that. And then find the sine theta. However, as a physicist, I don't like complex calculations. Yeah. Physicists are a bit lazy in that case. So I'm going to write tan theta. Tan theta is equal to 10 over 200, which is 1/20th. And I understand that theta is a small angle. Theta is small. Theta is small. And we know the small angle approximation that tan theta is approximately sine theta. So sine theta is approximately 1/20. Okay, so I'm approaching a math problem like a physicist. I'm not liking the complex calculations. If you actually calculate sine theta, it would be so close to 1/20 that yeah, because it is a small angle. Therefore, I simply put that this is approximately mg divided by 2 times 1/20, which is going to be 10 mg, and then whatever value for g I use. So it's 10,000 times g. No, let's say g is 10. So 10,000. So it's a million. Is it? 100 times 10 is 1,000. No, okay, it's 10,000, not a million. So 10 times 100 times 10. Yes, 10,000 newtons. And you can also realize that the tension in the rope is 10 times the weight of the mass, which is something quite, oh, it's kind of quite important to understand that in this scenario, because this small component, these two small components have to compensate the huge weight, the tension has to be quite large. Okay, so the tension is 10,000, is approximately 10,000 newtons. Yeah, is there a question? If not, please mute your mic. If there is a question, do ask. Okay, so that's the first question. The second question, find the center of mass of a quarter of a uniform cylinder, radius r, length L, and density rho. Again, there are different approaches to this problem. I'm going to use the straightforward approach. I'm simply going to say, okay, let's draw a quarter of a cylinder. So by quarter of a cylinder, I of course mean this. So it looks like this. This is a quarter of my cylinder, radius r, length L, and density rho. Okay, so I place my cylinder onto coordinate axes. Once again, you can choose the axes as you wish, as you see fit. There's no right or wrong way to place the axes. Just some ways give you simpler maths. So this is R. So this is R. So I'm going to split my cylinder. I'm going to cut my cylinder into vertical slabs in shape of a cuboid. So from this side, it will look like rectangles. Okay. I'm going to choose one of those rectangles. Let's say this one, and just analyze it. So I'm interested in this rectangle. The width of this rectangle is delta x. The height of this rectangle is y. At this point. So at this point is y. Now we need a relationship between x and y. Well, we started with a circle of radius r. So let's write down the equation of a circle of radius r. So x squared plus y squared equals to r squared. And from here, we get y squared is equal to r squared minus x squared. So y is equal to square root of r squared minus x squared. Of course, y is plus or minus square root, but because we see from the graph that y is positive, we choose the positive side. So we choose plus r squared minus x squared. So we don't have to worry about the negative part. Okay, so that is y. This is the height of the rectangle. Y. The horizontal position of the rectangle is x. Let's call it xi. Xith. It's the ith slab, ith rectangle. So let's find the area. So the area of this rectangle is equal to y multiplied by delta x. Y, okay, let's call it yi times delta x. And y is this. So it's going to be square root of r squared minus xi squared delta x. That's the area of the rectangle, because the area is width times height. So width times height is the area. Then we need the volume, because it's not a rectangle, it's actually a cuboid. Because if you look at it in 3D, it will look like this. It is in fact a cuboid. The volume of this cuboid is area times length. And the mass of this cuboid is density times volume. So it's density times A times L, which is density times L times square root of r squared minus xi squared delta x. This is the mass MI, mass of the ith slab. Brilliant. Now we need the formula. We need the formula for the center of mass. So we're going to find the X center of mass. We're not talking about the R center of mass, because that would be in 2D. We're just interested in the horizontal position of the center of mass. So let's write that down, horizontal position of the center of mass. And we have a wonderful formula for that. So X center of mass is equal to fraction M1 X1 plus etc. plus Mi Xi plus etc. plus Mn Xn over M1 plus M2 plus etc. plus Mi plus etc. plus Mn. Okay, but the ith mass is given by this expression. So simply put, we can find the sum of Mi multiplied by Xi divided by the sum of Mi. Okay, so that's that. We substitute Mi. We substitute this into the top one. We substitute this one into the top one, and we get the sum of rho L square root R squared minus Xi squared delta X multiplied by Xi. So multiplied by Xi. Now the bottom part is simply the sum of masses, but that's quite easy to find because we know the shape. The shape is a cylinder. So the sum of Mi is simply the total mass. And we know the mass is density times volume. And we know the volume. The volume is area times density area times length. So it's density times pi r squared over 4 times length. So we don't have to sum it up. We just can use the standard result. So it's density rho, then rho times pi r squared divided by 4 times L. Okay. So we haven't yet figured out what to do with the top bit, but you can guess. You can actually guess what to do with the top bit. And I have to say that this is approximate. approximate. I've mentioned it several times before because these are not exactly rectangles. I mean, the rectangle is an approximation. That's why it's approximate. But it becomes equal when we take the integral. So we have the x center of mass. X center of mass is equal to, now the limit when delta x tends to 0 of this expression. And the limit, we're using the Riemann sums. It's going to be, instead of the sum, we now have the integral. Instead of delta x, we have dx. So delta x changes to dx, xi changes to simply x. And we need the limits. And looking at the graph, the limits are from 0 to r. From 0 to r. 0 to r. And the bottom part doesn't change because there's no delta x. So it's simply a constant. Okay. Now, let's look at the integral separately and then substitute it in. So we're going to take the integral separately. Here. So what do we see? Well, first of all, I'm going to take the x and put it here at the start. X. And then I'm going to use a substitution. Substitution that u is equal to r squared minus x squared. This is my substitution. Then I find the derivative of du over dx. Du over dx. And I find the derivative. So the derivative of r squared is 0 because we're it's a constant. The radius is a constant, so it's 0 minus 2x. So from here, we get that du is equal to minus 2x dx. And x dx is equal to minus 1/2 du. Why did I do it like this? Well, because I already see that in my integral, I have x dx. Here it is. Look at that, x dx. It is already there. So from here, I can say s equal to integral. Now rho and L, they're constants, so they're going outside. And we have square root of u, and then du, and minus 1/2. So minus 1/2 goes in the front. Minus 1/2. Oh no. Minus 1/2. Now the only thing is the limits. Well, we need u1 and u2. u1 and u2, and we can find it here. So u1, so we substitute 0 instead of x. So u1 is going to be r squared. u2, we substitute r instead of x. So we're going to get r squared minus r squared, which is 0. So the limits are going to be from r squared to 0. Okay, so here I can take the minus and switch the limits round. So it's going to be 1/2 rho L, and okay, I'll copy it again. Square root u du, and it becomes from 0 to r squared. Okay. Right. I hope I haven't lost you. So I'm just going deep into integration at this point. So I get 1/2 rho L, and then the integral of u squared. So it's going to be u to the power 3/2, divided by 3/2, and between limits 0 and r squared is equal to 3 rho L. So the half cancels out, the 3 goes on top, and then we have r squared to the power 3/2. That's r cubed. Voila, that's a full stop. So that's the integral. The scary integral which we had initially just simply becomes this. And okay, so we plug that in here. And on the bottom, we have pretty much this. So now we just carefully simplify this fraction. So rho and L cancel out, r cubed and r squared cancel out, and we're left with 3r divided by 4 pi. If I'm not, that doesn't seem right. I think I made a mistake here. Oh yes, of course. It's not 3, it's 1/3. Yeah, the negative, I moved the negative inside and I flipped the integral limits. It's not 3, it's 1/3. 1/3. Like that. 1/3. So here. going to be 4r divided by 3 pi. I think that's right. Yeah, that's right. And that's the x coordinate of the center of mass. Now, by symmetry, you can understand that the y coordinate of the center of mass is also 3r over 3 pi. So the center of mass is here. And the x coordinate and the y coordinate are both equal to 4r divided by 3 pi. 4r divided by 3 pi. That's the coordinate of the center of mass. Okay. Can I get a quick vote on how well you understand problem 2 on a scale of 1 to 10 in the chat? Good. Oh, so many 10s and 9s. That's brilliant. For those of you who've got lower scores, make sure to watch my previous webinars just to get a hang of it, because I've done. Could you have used volumes? Well, this is not a volume of revolution. That's the problem. I mean, the cylinder is. The cylinder is. So, Jakub, for example, could you point out the particular part where I lost you, basically, where you got lost? Just let me know. I'll try to add a few more words there. Okay, moving on. Find the center of the 3/4 of a cylinder. Use the results from problem 2. So now we have 3/4 of a cylinder. Well, why not? So we have one cylinder, 1/4 of a cylinder, another 1/4 of a cylinder, and another 1/4 of a cylinder. Now, once again, we choose a convenient system of coordinates which you want to use. So I'm going to use this set of coordinates. Okay, so x and y. And I know that these 3 masses are identical. We know let's call this M1, M2, and M3. And we know that M1 is equal to M2 is equal to M3. And it's equal to area, so density times area times length. Density times pi r squared divided by 4, because it's a 1/4, times the length of this cylinder. Yeah, so once again, it's a 3D problem, but we're just looking at the 2D cross section. So the masses are the same, and now we need the coordinates. Well, let's say the coordinates of the centers of masses, not the coordinates, but the radius vectors. Yes, by all means, you could have a negative mass for this one. Absolutely. So I'm going to say that the position of the center of mass is R1, R2, and R3. I just want you to get used to this notation, that R is a position vector. And we have R1 is equal to my cheat sheet. R1 is minus 4R over 3 pi and plus 4R over 3 pi. That's the coordinates, because we know the coordinates of the center of mass of the first part. The first part is this bit. Yes, the second part is this. And the third part is this. Okay, so R1. The position of the center of mass of the second part is minus 4R over 3 pi and minus 4R over 3 pi. And R3 is 4R over 3 pi and minus 4R over 3 pi. Okay. If you understand everything so far in this question, type 1. If there's something you don't understand, type 0. Okay, good. R is the position of the center of mass of each shape. And now we simply use the formula for the R center of mass. Of course, you could use X and Y separately. I'm going to use the formula. It's going to be M1 R1 plus M2 R2 plus M3 R3 divided by M1 plus M2 plus M3. Now, because M1, M2, and M3 are equal, we can take it out. So we get M1 R1 plus R2 plus R3 using the distributive property of multiplication. And because M1, M2, and M3 are the same, we can say that M2 is M1, M3 is M1, and take M1 out. And the bottom part is 3M1 because they are the same. So M1 cancels, and we get 1/3 of R1 plus R2 plus R3. Already made my life easier, not having to substitute M. And finally, you get 1/3. You can notice that all the coordinates are the same. It's 4R over 3 pi. So I'm going to take 4R over 3 pi out of the brackets. And what I'm left with is very simple vectors, -1, 1. This is R1, because so R1 is 4R over 3 pi multiplied by -1, 1. I hope you understand that. So I'm just taking 4R over 3 pi out, plus R2, which is -1, -1, plus R3, which is 1 and -1. And we're left with, this is 1 over 3 times 4R over 3 pi. So it's 4R over 9 pi. And now -1 plus 1 is -1. 1 plus minus 1 plus minus 1 is minus 1. So these are the coordinates. So here we can see that the x center of mass is equal to minus 4r over 9 pi, and the y center of mass is minus 4r over 9 pi. What is the significance of this answer? Well, the center of mass is here. It's 1/3 of the way from the origin to this point. And in fact, one thing that you should realize that if we draw a triangle, then this is the median line of the triangle. And it is written in the assignment that the center of mass of a triangle is 1/3 of the way along the median line. So it's actually as if you had a triangle with 3 equal masses at the vertices, and you needed to find the position of the center of mass. And the position of the center of mass is 1/3 of the way, because this is 4r over 3 pi. So this is 4r over 3 pi, and this is 4r over 9 pi, which is 3 times shorter. So the x coordinate, well, minus, of course, minus. Okay. So I don't know. I find this very satisfying. I don't know how you guys. All right. Any questions here? I can answer questions just in case if you'd like me to. Okay, moving on to question 4. A uniform plate consists of a semicircle and a rectangle. Find the ratio h over r if the center of mass of the shape coincides with the center of the semicircle. Okay, this picture is not perfect, but the semicircle starts here and here. So the center of the semicircle is also the center of mass of the shape. Of course, we start with choosing a position for your x-axis. And I suppose the easiest way is to do it like this. So this is the x-axis, and this is 0. This is 0 on the x-axis. Now, a few things that you need to know. Well, the center of mass of the semicircle is a distance of 4r over 3 pi. And you can prove it using the previous example, previous 2 examples. You can actually prove that. It's a non-difficult proof whatsoever, but it's that. The center of mass of a semicircle is 4r over 3 pi away from the center. Using the same logic. The center of mass of a rectangle, of course, is h over 2 away. So this is minus h over 2 because it's negative. This is 0. And this is 4r over 3 pi in terms of, so x, let's call it, this is the first shape and this is the second shape. So x1 is going to be equal to 4r over 3 pi, and x2, the position of the second shape, is minus h over 2. Now we need the mass, m1, the mass of a semicircle. The mass of a semicircle is the area times sigma, where sigma is the area density, which we might know, might not, which we might need or might not need. But let's write it down. Everything we don't know, we replace with letters. So area is half a circle, so it's pi r squared over 2. So pi r squared over 2 multiplied by sigma. And m2, that is the rectangle. Once again, it's area times sigma. So area is going to be h multiplied by 2r, because this is 2r. So h multiplied by 2r multiplied by sigma. Perfect. And then we simply use the formula for the center of mass. Center of mass is m1 x1 plus m2 x2 divided by m1 plus m2. And we know that the center of mass is at the center of the circle. So the center of mass has a coordinate 0. Therefore, this is equal to 0. Multiplying both sides by m1 plus m2, we get m1 x1 plus m2 x2 has to equal to 0. So we kind of get rid of this bit. So if a fraction is equal to 0, that means that the numerator is 0. And here, so we substitute m1. So pi r squared over 2 sigma. x1 is 4r over 3 pi plus m2, which is 2 hr sigma, I'm slightly changing the order, multiplied by minus h over 2 equals 0. We can divide both sides by sigma. Not really necessary here. Okay, yes, divide both sides by sigma. Just get rid of sigma. So we have 4 and 2 cancel. So there's a 2. So it's 2 pi r cubed over 3 pi. Pi cancels as well. Plus, minus 2 cancels. So h squared r equals 0. So from here, we move on to 2/3. Interesting. Pi cancels, so we have 2 r cubed over 3 is equal to h squared over r. Dividing both sides by r, we're allowed to do that because r is not 0. So we divide both sides by r. And we need the ratio of h over r. So h squared over r squared from here is equal to 2/3. And okay, h over r is equal to square root of 2 square root of 3. Okay. Yep, that's about it. That's the answer. Center of mass is equal to 0. Why is the center of mass is equal to 0? Because that's what it says in the question. The center of mass of the whole shape coincides with the center of the semicircle. And I've chosen my x-axis so that 0 is here. 0 is in the center of the circle. Does it make sense, Francis? Oh, this question I really enjoyed. A sphere is held by a light string on the bottom of a tilted box, or a box that can tilt. The friction coefficient is mu. Find the maximum angle of tilt of the box so that the box doesn't slip. So just to be clear, when we say mu is the friction coefficient here between the ball and the surface, mu, and the string is held, well, let's say there's a small nail which is hammered into the sphere, and there's the rope is attached to this nail. Just to understand that we're on the same page, that we're talking about the same thing. Find the maximum. So as you understand, if I tilt the box, at some point this edge will slip, and the ball will hang from the rope. But in this, so the ball will end up like this at some point. But we are interested in the critical moment when it starts slipping. So as usual, we draw the forces. So we draw the ball and we draw the forces. So we have the tension force here, tension force. Then we have the friction force. I don't know the size of the friction force, but I know that when it starts slipping, it's going to be mu r. That is the critical value at which it starts slipping. So mu r, where r is the reaction force. Of course, there's the reaction force. Reaction force acting on the ball. Well, it is at this point. Actually, it does make sense to draw it from here. So from the point of application. Okay. So we draw forces from where they are applied, usually. And mg. Mg is a downwards force. It's not off center, I'm just drawing it slightly off center so that the lines don't intersect. Actually, mg is of course applied at the center. Mg. Right, time to choose our axes. And of course, when we have a tilted platform, we always have, well, X and Y. X-axis goes along the slope and Y-axis goes perpendicular to the slope. So I'm going to MG, I'm going to split it into two components. And this is going to be mg cos theta, and this is mg sine theta. And then we resolve, so we write the forces along the, I'll just duplicate that this is the y-axis, and this is the x-axis. This is the x-axis, this is the y-axis. Now, okay, so along the x-axis, we have t plus mu r has to equal to mg sine theta. And along the y-axis, we have r has to equal to, r is equal to mg cos theta. So we're resolving vertical forces, or the y forces and the x forces. So we kind of disregard this force because we've replaced it with two other forces. Hope that makes sense. If not, just do ask me a question. Don't hesitate to ask me a question at any point. So the reaction force R capital. Now, is there a problem here? Well, there is. There is. Let's see what the problem is. Let's count the variables that we class as unknown. We only know mu, and however, we have t, r, and theta that are unknown. Well, of course, m, but from experience, you know that when you're talking about tilting and the mass doesn't play a role whatsoever. Okay. And when I was studying physics, I was very interested in what makes a person go fast down a water slide, and everybody was saying that it's the mass of the person that affects the speed. The heavier the heavier person will go faster. But if you do the calculation, actually no, it doesn't play a role whatsoever. So in a water slide in a water park, it's the only thing that plays a role is what kind of swimwear you're wearing and how you're sitting. So it's the coefficient of friction that matters. The mass doesn't. And I hope I've managed to convince you in the previous assignments that actually no, when something is sliding down a slope, it's the only coefficient of friction that determines the acceleration. And here, so we can say that m is unknown. So the problem here is that we have three unknown values and only two equations, and that is a problem. That means you won't be able to solve it unless you have a third equation. So this is my fundamental approach. I look at what I have, I look at how many unknowns I have, I look at how many equations I have, and I understand that I won't be able to solve it because for 3 unknowns, I need 3 equations. No, the coefficient of friction. Okay, right, so let's say you have a water slide. You have a water slide and this is a body, and the coefficient of friction is mu, and we have the mg, of course, then the reaction force, and then there is the friction. So this is mg, this is mu r, and this is r. So assuming the person is sliding, so friction is mu r. So friction splits into 2 components. Weight splits into 2 components, and we have mg cos theta, mg sine theta. So we have r, because the person is not moving in this direction. R is equal to mg cos theta, mg cos theta, and the acceleration, so mass acceleration, Newton's second law, is equal to mg sine theta. So the person is accelerating down the slope. Ma is equal to mg sine theta minus mu r. Of course, it seems that acceleration is dependent on r, but let's go further. So ma is equal to mg sine theta minus mu mg cos theta, and m cancels out. So acceleration is equal to g sine theta minus mu g cos theta. So the only factor that you can change in this equation, so to change your acceleration, the only factor you can change is this, and this you can be changed by taking a certain position when your swimsuit is not touching the slope, or it's a material of your swimsuit. Basically, that plays a role, nothing else. Okay, so a 20 kilogram person could go much faster. Oil. Please don't. But yeah, potentially, if you have a private water slide in your backyard, you're free to do whatever you like. Not in a public swimming pool, please. Okay, anyways, going back to this, going back to problem 5. So X and Y. So we have fundamentally, we have 3 unknowns and 2 equations. So we need to find a third equation. Otherwise, we will just claim the problem is unsolvable. So moments, why not? So moments about any point. Well, the forces are balanced, so it doesn't matter which point to take. I'm going to take moments about the center of the sphere. Moments about the point A. Let's call it about A. And you can see that the moment of R is 0. So R times 0 plus mg times 0, because mg is applied at the center, times 0. Plus, now clockwise is r, t times the radius, minus mu r times the radius. And the moments have to be equal to 0. So the sum of moments is equal to 0. So the moments, the clockwise moment minus the anti-clockwise moment has to equal to 0. So this is 0, 0. So we have TR is equal to mu R equals, sorry. That's the thing. It does not, if the sum of forces acting on the ball is 0, it doesn't matter where to choose your pivot. If you choose the pivot about this point, about point B, you would have the same result. And the same result being T is equal to mu R. Oh, wait a second. Mu R times R, of course, mu R. Because R cancels, you get T equals to mu R. As an exercise, I do advise you to try taking moments about point B, and you will have the same result. If the object is stationary, you can take the moments about any point. Okay, so T is equal to mu R. Oh, that's an interesting turn of events. T is equal to mu R. And if you think about it, it has to be true. Because if they were not equal, it would be rotating. The ball would be spinning if they were not equal, because there are no other forces that can cause the ball to spin. Mg cannot cause the ball to spin because Mg is applied at the center. You can't spin a ball applying a force at the center. You have to apply a force offset from the center. And R, the reaction force, acts through the center as well. So it cannot make the ball rotate. You cannot make the reaction force, rotate a ball. Which is brilliant. The two forces have to be the same, and that makes life so much easier. That's our third equation. That's a third equation, and that kind of closes the deal here. So we get mu R, because T is equal to mu R. So the first equation becomes mu R plus mu R equals mg sine theta. R is equal to mg cos theta. So from here we get 2 mu R, so 2 mu mg cos theta. 2 mu mg cos theta equals mg sine theta equal mg sine theta. Mg cancels out, which is not surprising. Yeah, given our previous experience with questions like that. And we divide by cosine and we get tan theta. Theta is equal to 2 mu. 2 mu. Yep. And theta is equal to arctan 2 mu. This is the maximum angle at which you can tilt the box and it won't slip. Arctan 2 mu. Okay. So we have 3 more problems to go. They are somewhat similar. It's just more practice with integrals. More practice with integrals. So if you finish the integral part, and you think you're fairly confident with integrals, yeah, feel free to leave, but we'll finish in 15 minutes. So the first question, this is, well, you look at it and you try to think, what's the first thing that comes to mind? Well, of course, it's a product of 2 functions. Potentially, it could be an integration by parts. But when it's 2 polynomials, when it's just a function of x, it's more likely to be a substitution. But you can also look at it, oh, it's a binomial expansion. Do a binomial expansion to the 5th power and then multiply it by x, you get a polynomial of the 6th power, and then it's dead easy to integrate. It's a straightforward integration. I'm going to use a substitution here. I'm not saying that's the only way to do it. There are several other ways to do this integral, plus 2x. I just want to show how this integral becomes reasonably simple when you apply the substitution. So du over dx, you find the derivative of du is equal to 2. So du is equal to 2 dx, or a half du is equal to dx. And we're going to use this here. Also, we need to find x as well. So x from here is going to be u minus 3 divided by 2. So directly from here, I found x. So this becomes integral u minus 3 divided by 2. The main rule of substitution is that you have to substitute everything. Then it's going to be u to the power 5. And dx is a half du. So it's a half du. So take the coefficients out. So it's a quarter integral of, now it's u minus 3 times u5. So it's u6 minus 3 u5 du. And so I went, basically what happened is I went from this integral, which seems very difficult, to this, which is incredibly easy, by using a substitution. Okay. So this is going to be a quarter multiplied by u6 is u7 over 7 minus 3u5, so it's 3u6 over 6 plus c equals okay. I'm gonna do a trick here, which you might find useful. Instead of c, I'm gonna use 4c, because why not? Because c is an arbitrary constant. C can take any value, so 4c can also take any value. And you're allowed to manipulate manipulate it like this. And this comes in handy in the next stage when I open the brackets. So it's going to be 1 over 28 u to the power 7 minus, this is a half times the 1, so it's 1/8. So a quarter times 3/6 is 1/8 u to the power 6, and plus c. Okay. u to the power 6. And now you reverse substitute, so it's 1/28th, 3 plus 2x to the power 7 minus 1/8, 3 plus 2x to the power 6 plus c. Ta-da. That's it. And problem 7. Now this is a product of two. This is a product of two functions, and well, could be a substitution, although it's difficult to say what the substitution is in this case, or it could be integration by parts. I'm going to go with integration by parts. It's sometimes it is an educated guess. There's no strict rules that, oh, you have to apply this. As I keep saying, and as I keep repeating, integration is an art. It's one of the hardest things you will be able to do. And without being integrated, okay, the ability to integrate makes a good mathematician. Basically, a good mathematician is good at integrating, and it comes from experience. So here I'm going to use integration by parts. So u is going to be x. V is, well, we don't know. We don't know what v is. U prime, the derivative of u is 1. The derivative of v is cosine 1/4 x. So now we need to find v. So which function, when differentiated, gives you cosine 1/4 x? Well, it's going to be sine, definitely. And it's going to be 4 sine 1/4 x. If you differentiate this function, you get this function. You can check that because, well, because this is the derivative of this is that. And we use the formula of integration by parts. So it's uv minus integral of u prime v dx. So uv is x 4x sine 1/4 x, 4x sine 1/4 x minus the integral of u prime, so it's 1 multiplied by v, which is 4 sine 1/4 x dx, and limits from 0 to pi. Okay, so 4 we can take out 4, and we need to integrate sine 1/4 of x. So we leave this as it is. The first bit we leave as it is, 4x sine 1/4 x minus. Now minus 4 times the integral of 1/4 sine of 1/4 x is minus 4 cosine 1/4 x. So it's going to be plus 16 cosine 1/4 x. And all of this between limits 0 and pi. So we substitute pi, we get 4 pi sine pi over 4, pi over 4 plus 16 cos pi over 4 minus 4 times 0 times sine 0, so 0, and minus cosine of 0 is 1, so it's minus 16. Minus 16. And this is sine pi over 4 is square root of 2 over 2. So it's going to be 2 pi square root of 2 plus 16 times square root of 2 over 2, which is 8 square root of 2, and minus 16. And that is the answer. Of course, if you wanted to do the answer to 3 significant figures, you could do it. But I'm going to leave it like this. Can't really simplify it from here. Okay. Any questions about problem 7? Any questions about problem 7? And problem 8. Now, problem 8 is a tiny bit problematic because it involves the integral which we were talking about in the very, very beginning. So it's once again integration by parts. So u is equal to x. If you have x times a function of x, usually it is an integration by parts. 1. When you're doing A levels, they tell you that it is, use integration by parts. V is equal to tan x. Oh, okay. V prime is equal to sec squared x. And we know that the derivative, sec squared x, is actually the derivative of tan x. Tan x, because tan x is sec x. Don't really have too much time to explain this because I want to focus on another thing. Actually, it is useful when tan x. No, sorry. This is if you don't know that the derivative of tan x is sec squared x, do it as homework. It was in the assignment, in the 3rd assignment. Anyways, we replace that, so it's going to be uv, so x tan x minus the integral of u prime, which is 1, multiplied by tan x, so by v tan x dx. And the problem is that we haven't done tan x, the integral of tan x, and we've never asked you to find the integral of tan x. And there's a good reason for that. The good reason being that we haven't done the logarithms yet, and this involves logarithms. Let me show how you can find the integral of tan x. Integral of tan x. It will require a substitution. So you get integral of sine x dx over cos x. Now, my substitution is going to be u is equal to cos x. So I kind of substitute the thing. Sorry. So you need to substitute something that you cannot integrate straight away, but you can integrate if you make the substitution. It's tricky to explain, okay? And with limited time, just assume that I know what I'm doing and I've done the substitution u equals cos x. I immediately find the first thing you do when you do a substitution is you differentiate u, and it's equal to minus sine x. Yeah. That means that du is equal to minus sine x dx. Oh, that's a nice coincidence because we kind of already have that here. Here it is. So minus du is equal to exactly that, sine x dx. And that's my substitution. So it becomes minus integral of du, du, and then 1 over u, 1 over u du. And in the beginning of this webinar, we discussed that. We discussed that the integral of 1 over x is logarithm modulus x. That's exactly what we're going to do here. It's going to be minus logarithm, natural logarithm of u plus c. Do a reverse substitution minus. Don't worry if you haven't done logarithms yet. You won't come to this. There are no logarithms in the assignment whatsoever, so don't worry about this. Cos x plus c. So we have found the integral of tan x, and all we need to do is just substitute that into here. So x tan x minus logarithm, so it's going to be plus logarithm cosine x. The modulus is a big deal here because cosine can be negative, but you cannot take logarithm of a negative number, plus c. And that's the answer. All right. When are going? What do you mean? Sorry, Abate. Which assignment? It's already up there. It's physics 04 and maths 04. It's already online. It's been online for, the maths has been up online for a couple of weeks, and the physics has been online. They're due in 2 weeks, less than 2 weeks. You got about 10, 12 days to finish them. So please find them if you haven't already. All the videos are also uploaded, and this video will be uploaded in the next couple of hours. So yes. Okay. Just another thing with your tutors. You can ask them to. So if you feel you need more support on the future assignments, do ask to go through some extra questions on a particular topic. Don't be shy. They will always go forward and help you. And I will be sending your tutors extra questions that you can go through. So yes, please do. Right. Well, I can check that. Wait. Okay. But you can text me on Telegram. I can check for you. I can check what's going on. You should have done, if you have done the first assignment and you got into the program, then you should have a tutor. If you didn't pass the first assessment, then you can carry on coming to these webinars, but you won't be able to have a tutor. So just text me in the group and I will check for you. Okay. All right. Nope, that's it for today. That's it for today. Right. Have a lovely week, and I'll see you next week, where we're going to do more integration and more problems on centers of mass. Centers of mass, especially, I want to do some movement of center of mass. Like it's like the question with the fly, fly in the tube. Right. See you. You're welcome.